Okay, now we've got a different situation, a roller coaster. We've still got a situation where we've got a weight, mg, there's mg, and now we don't have a tension, we have a normal force, right? Those are the two forces at the top, because the track will apply a normal force. Oops. And that we'll just give that label over there as the normal force. There we go. And those are the two forces. How about the free body diagram at the top? Well, let's bring those two forces over. You've got the weight force. Oops. You got the weight force. Okay. And you got the normal force. Those are the two forces on the. Okay, we do a free body diagram. Let's get the label. So that are the two forces. So they provide the centripetal force because they're pointing towards the center. So let's do the sum of the forces equal ma, which equals mv squared over r. There are two positive forces. Why? Because they go towards the center. So the weight and the normal force provide the centripetal force, which is mv squared over r. Let me see. What are we even solving for? Let's see. Find the normal force at the top. Excuse me. So the normal force in the top is the centripetal force, the force that's causing it to go in a circle, minus the weight force. So the normal force at the top was helped by the weight force. So there you go. It's less at the top, and you could expect that, wouldn't you? That on a roller coaster ride, that the normal force would be actually less at the top, and now it's greater at the bottom. Just like the other example, the normal force is going to be greater at the bottom. Remember, what this does not say is that we've got a situation where our speed is constant. Let's put that down. I should have stated that. Speed's constant, r is constant, mass is constant. We have a centripetal force that's constant, but we don't have a normal force that's constant. Velocity is constant. Okay, let's look at the bottom. Okay, we'll say that this is the bottom. Let's label it. What are the forces there? Well, maybe I shouldn't do that because we've got forces. So we've got on the bottom we have a normal force and a weight force. Let's put the weight force on first. Of course, we have a weight force and we have a normal force. Now, at the bottom, the normal force has to be bigger. Why? Because then there'd be no, if they were equal, there'd be no centripetal force, no net force towards the center. So we've got a weight force and we've got a normal force. And the normal force has got to be bigger, else we have no centripetal force, a force acting towards the center. All right, let's do the math on that. The sum of the forces, and remember, what's the positive force? This force that's on the bottom that's going towards the center, that's the normal force. So this is the positive direction, towards the center is positive. So sum of the forces equal mv squared over r. What are the positive forces? The normal. What's the negative forces? Minus mg equals mv squared over r. So the normal force is bigger down here because it's the force that's causing this thing to go in a circle plus mg. So just like before, let's look at these two equations. The bottom is once again bigger than the top by 2 mg. All right, the normal force on the bottom, because this is minus mg, this is plus mg. What's the difference between minus mg and plus mg? Think of a number line. Minus mg plus mg. What's the difference between that? That's 2 mg. So the normal force on the bottom is bigger than the top by 2 mg. Maybe you can write that down. F normal bottom greater than F normal top by 2 mg, or twice the weight of the car. Here's another similar situation that we had before. What's the minimum velocity required for the roller coaster to prevent the passengers from falling off? That's another way of saying maintaining that circular motion. The minimum velocity, so write down min velocity is where in a roller coaster, F normal equals 0. Where, what does that mean? Only the weight force is actually providing, that's the minimum force. Your weight force becomes your centripetal force. So, normally, it's Fn plus mg equals mv squared over r. That's the general equation. But you're at the minimum velocity when you have no normal force, and mg equals mv squared over r. And just like before, the m's cancel out. We cross multiply. We get gr equals v squared. So at the minimum, you better not go any slower than this, or they're falling off. Radical gr. Okay. So always at the minimum acceleration is where g equals v squared over r. Okay. Minimum velocity occurs when v equals radical gr. Alright, so now this is a difference, still the same, but this you're going to find a different situation here. Where this is just now a hill. We all know that you can go just so fast. If this guy goes too fast, he actually leaves the hill, right? If you go like 200, 300 miles an hour, he just goes this way. He loses contact with the ground. So find the normal. Let's not worry about that. Let's find the normal force. So it goes like that, and the weight force goes like that. Now notice that the weight force absolutely should be greater than the normal force. How else could it go in a circle if the weight force is not greater than normal? Let's put the labels here, and there you go. That's what it looks like. So what is this? So the positive force is the weight force because it's going towards the center. Let's get our physics points right away and write sum of the forces equal ma. The positive force is mg going towards the center. The negative force is the normal equals mv squared over r. So what we find is I could put this on the other side. So mg equals mv squared over r plus normal. And so the normal equals mg minus mv squared over r. Now that's different than what we've been seeing, that the normal is the weight force minus the mv squared over r. So if you go over a hill really fast, don't you feel a little lighter? You feel like the normal force would be the seat's force on you. If you've gone over a hill very fast, you can actually go over it so fast that you just don't feel any weight at all. You don't feel any pressure from the seat. So the question is, at what speed will the car leave the road at the top of the hill? What minimum? It should be what minimum speed? Yeah, what minimum speed? Let's add minimum. So that's where the normal equals 0. Let's write when normal equals 0. And that's when if you go on a roller coaster pretty fast, you get that sensation that there's no, they also call that the apparent weight. There's no force from the apparent weight. It's the weight you feel from the seat. So you can get into a state of weightlessness when you're going so fast that you feel a sense of weightlessness. So remember that. Let's put a star next to that. It's a big deal right there. On a hill, let's write hill. It's not a roller coaster, it's the hill only. When the normal force equals 0, and when your apparent weight, you feel like you're 0. You don't feel any pressure from the seat. So let's make the weight 0. And we can see that mg, if this is 0, then mg equals mv squared over r. And once again, there's that equation again, that v, cross multiply, v equals radical gr. So all of these limit situations or v equals radical gr, limit being like how, and now this is this is not a minimum, this is a maximum speed. So actually, this is the minimum. See what minimum? So yeah, no, that's the minimum speed that if it's v or that velocity or greater, right? That velocity or greater, you leave the road. That velocity or greater, you leave the road. So you better not go any faster than that velocity, or else you lose contact with the road. Let's write that down. If you lose contact with the road. And that, I think, is it. Yes, it is.